Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials for Tank Engineers, Part 4 on Stress Transformation. In this module, we will start to talk about stress transformation. This means rotating a stress element to a new coordinate system so that we can evaluate and understand the stress state, which is the shear stresses and normal stresses based on the stress element orientation. As you will learn here, the magnitude of the shear and normal stresses vary with the orientation of the stress element. Because materials typically fail by exceedance of either a normal or a shearing stress, it's important to have a systematic way to identify what the maximum of both the shear and the normal stresses are, in addition to their orientation and direction. I would urge you to watch the two videos listed here to see some of the animations that explain in detail how this works. The great mathematicians Leonhard Euler and Cauchy both played key roles in the development of modern stress analysis. Euler, who may be the greatest mathematician who ever lived, stated, "A difficult concept is the idea of forces and stresses acting inside a material within the interior where neither eye nor experiment can reach." But Augustin Cauchy, who almost single-handedly developed the modern theory of analysis, or the theory of calculus, was the key to providing the current perspective on stress analysis in a paper he submitted to the Scientific Society in 1822. We see in the diagram concepts that we've seen before. A uniaxial stress results in a normal force F and a normal stress sigma, which is equal to the force divided by the area. And finally, the normal and shearing stress are dependent on the angle that an imaginary cut plane makes with the axis as indicated here. We will now quantify these effects. Here we have a bar in uniaxial tension. The axis is aligned with the forces shown. The cut plane in a free body diagram is typically taken normal to the axis, this vertical line, but it can be taken at any angle theta. In fact, that is what we intend to show, what the basic relationships are. N is the normal force. That always points perpendicular or normal to the cut plane. V is the shearing force. That's parallel to the cut plane. Sigma x is the stress in the x direction, which is aligned with the axis. And A prime is the area of this slant plane, whereas A is the area of the cross section. If we look closer at these relationships and angles, what we have is the sum of this cut plane angle theta and the complement of this 90-degree angle. Because these two lines are parallel, we can say that this angle here is gamma. And because gamma and theta add up to 90 degrees, and in a triangle we have 180 minus the 90, this angle must be theta. So theta plus gamma is equal to pi over 2, or 90 degrees. The force F can be resolved into components on the cut plane, which is angled at theta, and we have F cosine theta for this vector, and we have F sine theta for the shearing force, V. Those are shown here. Sigma x, the normal force along the axis, of course, is just F divided by the cross-sectional area. And if we look at the relationship between the cross-sectional area A and the slant plane area A and the angle theta, we have from elementary trigonometry, A prime times cosine theta is equal to A. If we plug that relationship into here, where we take the normal force on this area, which is A over cosine theta, then we can see that sigma theta, which is the normal force on cut plane at angle theta, is F over A times cosine squared of theta. So this is the same as sigma x times cosine squared of theta. Similarly, we can take tau theta, which is a shear stress on the cut plane at angle theta. It's V divided by A prime, and we end up with sigma x sine theta cosine theta. It's useful to plot these functions as we rotate the cut plane. So this cut plane is vertical, represents the cross section when this angle theta is 0. As we rotate this angle first to pi, or 180 degrees, we go along here to pi over 2, which would be aligned with the axis, and then we continue to pi, where this vertical cut plane would be rotated 180 degrees, and then we continue around and it returns to its original position. Here I'm going to just plot the trigonometric functions. The sigma x is just a scalar that allows you to get the actual stress, but let's look at the interesting part, which is cosine squared theta and sine theta, cosine theta. There are a couple of features that stick out when you look at this. First of all, the frequency is doubled in both cases, and we'll show you why mathematically on the next slide, but for now you can see that this goes through a complete cycle, goes from 1 to 0 and comes back up to 1 at pi, which is just a 180 degree rotation. It does that again as the plane gets flipped back up to the vertical position. The red line, of course, is a plot of the cosine theta. Note that also what this does is take any negative values, and a negative times a negative is a positive, so all values are positive. This says that the normal stress on the cut plane is always positive, oscillating between its maximum value 1 down to the minimal value. Of course, it gets multiplied by sigma x. If we look at the shear stress trigonometric function here, sine theta, cosine theta, a couple of features stick out. It has the same doubling of frequency effect here, but what it does is it is only half of the magnitude. It's 0.5, so the maximum value of sine theta, cosine theta is 0.5, but it also goes from positive to negative to positive, and it doubles in frequency also. These two functions are plotted here. The green is if you multiply by sigma x, the axial force or stress. Sigma theta, which will be the normal stress on the cut plane, is oscillating like the green line, and the shear stress is oscillating like the red line. One other thing to note is that the peak of the normal stress starts out at 1. That means the maximum normal stress is aligned with this axis in the same direction as the forces, but shear stress is 0 at that point. That's when this plane is vertical. As a plane falls over sideways and is aligned with the axis, of course, then we have 0 shearing stresses again and 0 normal stresses. Notice that at pi over 4 we have a maximum shearing stress. Pi over 4 is 45 degrees, so this is about 45 degrees. That's where the maximum shearing stresses occur. The two equations are listed here. So the normal stress is equal to the axial stress, or the normal stress on the uniaxial axis, times cosine squared of the rotation. Tau, the shearing stress on the rotated plane, is equal to sigma x times sine theta cosine theta. From these two trigonometric identities, so for example, this first one, you can just substitute cosine squared theta with 1 plus cosine 2 theta over 2, and you get this formula. What this shows is that sigma theta is a function of cosine of 2 theta, and that's how you get the doubling of the frequency. You can do the same thing with a sine function here and substitute into the shear stress formula, and you'll end up with a similar function, except it's a sine function of 2 theta, which doubles the frequency. The maximum shearing stress, though, you can see because of this divisor here, is only 1/2 of the maximum normal stress. To summarize the key points, we have that the maximum shearing stress is 1/2 of the maximum normal stress. If we again look at the diagram, theta equals 0 represents the cross section, since we're measuring theta as this angle here. Sigma max occurs at theta equals to 0, as you would expect. The maximum normal stresses occur across this vertical cut plane. Now, tau max, the maximum shearing stresses, occurs at 45 degrees, pi over 4, like this. As we rotate the plane, you can see that when we get to 180 degrees, or pi, everything repeats after this point, so there's no new information. This is because the frequency has doubled, as we discussed earlier. In some of the tensile test videos that I recommended, they talked about Luder's lines. Those are these striations that occur when you pull on a tensile sample, even though the normal force, the maximum normal force, is in the x direction along here. The slippage, the failure of the material, occurs at a 45 degree angle. That is because most ductile materials have relationships similar to what I showed, in that their maximum shearing stresses, under which condition they fail, occurs at 45 degrees. Next time we'll do a little bit more work on stress transformations, and then we will get into the Mohr circle. Thank you.